Hi everybody, welcome to your first video. This is a review specifically for material for break, where I'm really just going to be focusing on the derivative, and again, just kind of reminding you what it is. I'm not going to go into great detail for what it is, but this is going to be kind of the world where we're going to kind of stay in. If we have a function f of x, so f of x can be any kind of function we really want to kind of look at or focus on, then its instantaneous rate of change is f prime of x. This is the derivative. Spelled derivative wrong. Derivative of f of x. And again, what f prime essentially represents is how the function is changing at any specific moment, thus the instantaneous part of this. And so I've got actually a function pulled up with Desmos where the blue function, this parabola, is my f of x. And this purple point right here represents essentially how the curve is changing at any moment. And so notice that essentially as I get closer and closer and closer to the vertex, where the graph is slowing down and begins to stop changing, notice how like flat my slope is. So specifically around 3 comma 1. There we go. My flat is the line is perfectly flat because we've reached the rock bottom. And this kind of makes sense a little bit more, if I start on the far left, if I'm talking about or describing the graph itself begins to flatten out as I travel from left to right until I hit the bottom, and then it begins to increase, and you'll see the slope get steeper and steeper and steeper in the positive direction as I'm going up. And so what the slope is the derivative. It's f prime. And so just kind of going back to this, we had a limit definition, which was pretty wild. It essentially said for a function f of x, if I want to find f prime, I need to do the limit as h approaches 0, and then I would need to do f of x plus h minus f of x all over h. And this involved a lot of work, which was bad because it was really, really, really long. It took a lot of steps to go through and do, and so it just took a lot of time. And it's the time that we want to try to essentially avoid by looking at derivative rules. These are the shortcuts. These are the steps that we want to do every single time. And the first rule that we had was the constant rule, which essentially says if I want to find the derivative, which is notated as dx, d over dx. So again, what this notation stands for is find the derivative of what comes after it. So find the derivative of a constant c. And c again can be this can be any real number right here. So any number that you can think of. If I derive a constant, this derivative is always going to be 0. And we talked about in class, the reason behind that is if you are remaining constant, aka you are not changing, I'm staying along this straight line, then my rate of change is constant. I'm not changing. We represent a no change with the number literally of 0. And so this again is the constant rule. And from this point on, we then looked at what's called the power rule, which said if I want to take the derivative of specifically x to the n, where n is a real number, then the derivative is nx to the n minus 1. Essentially saying that you're going to take whatever power is in the top and it's going to come to the front, and then we subtract 1 from that power. And so an example would be if I want to take the derivative of x to the 5th, then this derivative would be 5x to the 5 minus 1, which is 4. And so this would be the derivative of x to the 5th. 5 comes to the front, and then subtract 1 from the power, which we can see. 5 to the front, subtract 1. And so that is our power rule. And so we have constant rule and power rule. But we also have the derivative of a couple of operations. So just to kind of scroll down, we essentially have the addition and subtraction rule, which says if you want to find the derivative of two functions being added or subtracted, then to find this derivative, we derive the pieces individually and then add or subtract. So for example, let's say we had something like x to the 5th minus x to the 3rd. So I essentially have two power rules. Well, if I want to find the derivative of this, of x to the 5th minus x to the 3rd, I'm going to go through and derive these pieces individually and subtract the results because it was subtraction to begin with. Now, when I go through and do these derivatives, I can only use the rules that we already know. So for these addition and subtractions, as of right now, I can only go back and apply the shortcuts if I have a constant or if it's a power rule. Well, for me, this is x to the 5th. This is a power rule. And this is x to the 3rd, which is, again, a power rule. So I can go through and take these derivatives using this setup. Derivative of x to the 5th is 5x to the 4th minus derivative of x to the 3rd, 3x squared. And so this is the addition and subtraction rule. We also talked about, at this point, the scalar multiplication rule. And scalar just means a multiplier. So you're essentially taking your function, whatever we have, and multiplying it by a constant. I'm scaling it by a certain value. And so mathematically, that would be just straight up multiplication. And that rule would look something like this. I want to take the derivative of a constant times a function, which I'll just call f of x. And when I derive something like this constant, if what I'm looking for is essentially the rate of change, how a slope is changing on this curve, when I multiply this function by a scalar, I'm stretching those slopes by that same factor. And so what that means is this derivative would be the same thing as if I just found the original derivative for f and scaled it appropriately, whatever that value of c is. So for example, again, looking at x to the 5th, if I was to scale that by 5, so I have a function that's 5x to the 5th, what this 5 is doing is it is scaling all of the original rates of changes for x to the 5th by a factor of 5. So if I wanted to go through and apply this rule, I would go through and say 5 times the derivative of x to the 5th, which again, x to the 5th is a power rule. So this is 5 times 5x to the 4th, which is 25x to the 4th. There is my derivative. There's my rate of change. And what's really important to remember here, and just recall in terms of information, is that this whole step right here is pretty trivial. Same thing with this step here, because what I can end up doing is, because this 5 right here is just being multiplied in front, when I bring the power of 5 down, notice how it ends up just multiplying with what was in front. So 5 times 5 is 25, and then I take 1 off the power. And so we can do this anytime there's a scalar in front. It's just hanging out. If we end up needing to multiply it by any number that comes down, we can do that. Otherwise, that's what we have. And so this was the first set of derivative rules that we talked about. Again, the constant rule, so anytime you derive a number, that number has a derivative of 0. We talked about the power rule. This is the main building block. Anytime we have x to the n, we have addition and subtraction. So this allows us to create more complex functions, something like x to the 5th minus x to the 3rd, and allows us to then find that derivative and how that function is changing. And then we have the scalar multiple. This allows me now to have coefficients and be able to go through and derive. And so this really kind of opens up the door now for specifically polynomials and how I could go through and find the derivative of polynomials. Keep in mind, a polynomial is something that's like 3x to the 3rd minus 2x squared plus 10. Right? It's just something that has x's with whole number powers and then real coefficients, like 3 minus 2, and 10. And so let's just go ahead and call this f of x. And so if I want to differentiate this, if I want to find f prime of x, then what I want to do is I'm going to go through and derive f, which is all of this. So I want to take the derivative of 3x to the 3rd minus 2x squared plus 10. And what I'm going to kind of walk you through again is kind of the long approach of this. And again, you can skip a lot of this, and y'all are already at this point. Y'all have picked up on this pretty quick. But just to walk through it again, when I'm taking the derivative of this overall thing, because of the addition and subtraction rule, so addition and subtraction, I'm allowed to break this up into 3 individual derivatives. The derivative of 3x to the 3rd minus the derivative of 2x squared plus the derivative 10. And now I'm going to go through and derive these 3 individual pieces. This derivative is the scalar multiple with the power rule. 3 will come down to the front, so I'll get 9x squared. Now minus here, this 2 come down to the front and make it 4x to the first power. And then again here, and this is where you got to be very, very careful, the derivative of a constant is always 0. Now this step right here is always trivial, so you technically don't need to write this. So anytime you have a constant, you can just say that the derivative just goes, the derivative of it makes it go away. The derivative is 0, so it's gone. And so in conclusion, we have that f prime of x is 9x squared minus 4x. We don't need to write to the first power because that part's pretty trivial. And so what this function represents then is the slope of f of x at any x value. And so it allows me then to go through and find the slope of the curve anywhere I want. So let's just say, for example, I want to know, find the slope of the curve at x is equal to 1. So just a simple kind of value here for f of x is equal to 3x to the 3rd minus 2x squared plus 10. So the function that we were just looking at. So if I want to find the slope of the curve at x is equal to 1, the slope of the curve is asking for what is f prime at this x value of 1. Well, we know f prime f prime, we just found it here. And so I'm looking for f prime of 1. So I'm going to take 1 and I'm going to plug it in to my derivative. So 9 times 1 squared minus 4 times 1. This comes out to be 9 minus 4, or 5. And so what this 5 again represents is the slope. And there's a lot of things that we can glean from this in terms of information, because we know with slope, the larger the number and magnitude, the steeper it is. So a value of 5 is telling me that I have a slope of 5 over 1. I'm rising 5, I'm running 1. I'm going up higher than I am to the right. And so I know that the graph is increasing fairly quickly at x is equal to 1. I also know, because it's a positive 5, that my graph is increasing and I'm traveling in this direction. My graph is going up. And so this stuff is going to be really important. We're going to look at it more at the end of this mod when hopefully we are back together again. We can work about this in class and in person specifically. And so that's the slope of the curve. Now, what the slope of the curve is called, because it's such an important concept, is this is the slope of the tangent line. So any kind of question, again, that's looking for the slope of the tangent line, what you need to do is take the derivative. So find the derivative as a function, and then wherever they want you to find the slope at, you plug it in like we just did. And hopefully you kind of remember this. If not, let me know. We can work on it more together, either as a class, since there's not many of us, and we can do that through Zoom, or we can do this one-on-one. Just let me know, and we can talk more on that, because we do have 3 other derivative rules to review with this stuff. Excuse me. All right, and so those other 3 rules to take a look at now are the product rule, the quotient rule. I spelled that completely wrong. I think. And then the chain rule. Chain rule was the very last thing we talked about. Now, product, quotient, and chain are essentially the other 3 main ways, specifically algebraic ways, to combine functions and create new functions. So if you notice, again, the way that this is stepped through logically is we started with the most basic function, which is a constant. We then said, okay, well, what if I actually have an x? Well, there's the power rule. Well, what if I have some kind of adding and subtracting of x's? Well, that creates polynomials. And scalar then allows for the coefficients on polynomials. But we know that there are more functions than polynomials. And so one of the ways that we can go through and look at a combination is through multiplication. So if I have 2 functions, so let's say we have f and g, and what I want to do with these 2 pieces is I want to multiply them together. Thus, product rule, right? Product stands for multiplication. And when I take these 2 functions and multiply them together, I'm ultimately looking for how that product is changing. I want to look at the derivative of this product. And what the product rule tells me is the combination is pretty crazy. It's something that you're going to need to remember. But that derivative rule is derivative of f times g plus the derivative of g times f. So this is the product rule in terms of the steps. I'm going to kind of slide it over just a little bit to kind of get it out of the way. And so it kind of makes sense then that I'm going to kind of move these down a little bit. And so then it kind of makes sense. If we have a product rule, then we must have a quotient rule. Well, recall a quotient in terms of a combination is division. So if I have a function f and a function g, and I wanted to divide these two pieces, and so I have f of x divided by g of x, and not only that, but I want to know how is this combination changing? What is its derivative? Well, the derivative is a little bit more complicated, but it's very similar to the product rule in that you derive the top times the bottom minus the derivative of the bottom times the top. And then you divide this by the bottom squared. And so how you'll generally hear this read is f prime times g minus g prime times f all over g squared. And this is the quotient rule. Now, the chain rule is a rule for a composition of functions. Just as a reminder, if you have a composition, you are composing one function with the other, which means you're taking a function, say g of x, and I'm plugging it in to f, whatever f is. And most of the time when you have a composition of functions, even when you can kind of tell from the notation, but there are always parentheses because the parentheses will denote what's being plugged in to what. So the F represents what is happening on the outside of those parentheses. The G is what's happening on the inside. And so when I have a composition of functions, something like f of g of x, and I want to know how is this composition changing, I find this derivative by doing the derivative of the outside first, leaving the inside alone, and then multiplying or chaining it with the derivative of the inside, which is g prime. And so this is the chain rule. And so what we then have is the last remaining three rules that we know of before the break, which again is the product rule, the quotient rule, and the chain rule. And we worked on these in class, I think up to Monday before interim. And then Tuesday, Wednesday, we kind of took it easy, kind of looked at a couple problems. And so what I want to do is I'll kind of give you an example of each one, just so you can see again how it kind of works. And then attached to this on your calendar, you'll see some practice problems. It's really just going to be, I think, a summary from the textbook we have. And you can go in and attempt some of these questions if you just kind of want to review. And if you get stuck on any of them, let me know. I will try to post some answers for it tomorrow. I think I should have plenty of time. I'm going to be trying to make videos and catch up, which takes a little bit of time. But that's kind of my overarching plan. So let me give you an example of each, and I'm just going to kind of follow through with the order that we have them in. I'm not going to try and trip you up. So here are the examples. Now feel free to write these down, pause the video as I go example by example, and then you can go back to the rules and try this on your own, and then check as we go along, because I know y'all like to do that. But I still want to kind of talk through them, and that's the great thing about the video, is that you can pause it and try everything on your own. You don't have to just watch it straight through. And so for both of these, I'm just going to use the same two functions so you can see how the composition and stuff kind of works. So let's say that f of x is, let's just say square root of x, just to do something that we haven't fully seen in this video yet. And let's make g of x something pretty straightforward. Let's say x squared minus 3x. So something like this. Now, before I get started, let's just remember that for f here, what makes this tricky is that a square root is a power. This x on the inside has a power of 1, and a square root is an understood 2 on the outside. And how I write that as a fraction is here. X to the first over 2, the 2 representing the square root there. And so we have x to the 1/2. And this is really important because notice that when I derive something that is square root, like in this problem right here, when it comes time to do it, we're essentially applying the power rule. It's kind of a hidden power rule there. All right, and so let's first look at if I want to do the derivative of f of x times g of x. So this is trying to find the derivative of the square root of x times x squared minus 3x. So it could look something like this in the grand scheme of things. So when I want to derive something like this, we're going to follow the product rule. Well, the product rule tells me to derive the first. So in this kind of case, the product rule is f prime times g plus g prime times f. All right, well, I could come up here. I'm not going to write this in blue. Well, f prime is equal to 1/2 x to the negative 1/2. Again, incorporating my power rule, 1/2 comes to the front, and then I subtract 1, which you'll see negative 1/2. My g prime is just two power rules. Derivative of x squared is 2x. 2 comes down, subtract 1, minus 3x is just minus 3. And so since I have all the pieces now, then I just need to follow the appropriate rule. So for product rule, my derivative will be f prime, which is 1/2 x to the negative 1/2 times g, which is x squared minus 3x, plus g prime, which is 2x minus 3, times f, which is x to the 1/2, or square root of x. Either one is fine, and here is my derivative using the product rule. If I am doing the derivative of a quotient, let's say f of x over g of x, I won't write the rule out this time. You can look back in the notes, skip back a little bit in the video. If I want to find this derivative, I want to find the derivative specifically of square root of x divided by x squared minus 3x. And to take this derivative, very similar to the product rule, I'm going to do f prime, which is 1/2 x to the negative 1/2, times g minus g prime times f. So again, you can kind of see how this is the exact same, barring the sign change in terms of the addition versus subtraction. And for the quotient rule, this is all over the original bottom squared. So my g, x squared minus 3x squared. And we can leave this. We will not simplify this any further. That's it. So don't be tempted. Right here, I'll highlight it. X squared minus 3x, x squared minus 3x. You're going to want to generally try to cancel these, but don't do it because in a fraction, remember that whatever my denominator is, so like in this case, the x squared minus 3x here, not only needs to be able to divide into this expression, it needs to go into this expression as well. And there's no x squared minus 3x over here. There's nothing to cancel it out, so I can't do it. People always tend to want to say like, okay, well, I see these here, so they must cancel. And that's not necessarily true. So just be careful with that, which is why I don't want you to really simplify this any further. That is my final answer when looking at the quotient rule. Now for chain rule again is a composition. So to kind of show you how that composition would work, let's say I want to do the derivative of f of g of x. So again, what this is referring to here is I want to take g and plug it in to f. So this would say take the derivative of the square root of x squared minus 3x. And so this is where the chain rule, we can kind of look at it again. It needs to have parentheses. Generally, these problems will always have parentheses, but we don't really have parentheses here, like I was kind of telling you earlier. But we can remember we can write square root as a 1/2 power. And because I have multiple things on the inside, specifically x squared minus 3x, I do have ultimately x squared minus 3x in parentheses to the 1/2. And so this is how, again, you can always kind of notice that something is a chain rule. I have an inside, which is x squared minus 3x. I have an outside, which is to the 1/2 power. And so to do chain rule says to do the derivative of the outside. Well, that means this 1/2 here. It's a power rule, so the 1/2 will come down to the front. My g doesn't change. The inside will stay. I need to finish the power rule by subtracting 1. So 1/2 minus 1 is negative 1/2. And then I chain it by now focusing on the inside. And so I'm going to only focus on the x squared minus 3x portion here now. And I'm going to derive it. And that derivative, which is g prime, is 2x minus 3. We've done this one, that derivative already. And so I can kind of write it, and then I'll kind of highlight it here. So again, this piece, I'll only derive it at the end. And so we talked about with chain rule, you're always working your way outside in. And so here's an example of that. And then we can leave this just like we did before. This is my overall answer. We don't need to simplify it any further. And so that's it for our review. Pretty straightforward, not super long, nor am I showing you a ton of examples since we did so many earlier. Product, quotient, and chain, I think, are the more difficult ones where you may want to practice a little bit more before digging into the newer material. Hopefully everybody feels really comfortable with doing the slope of the tangent line, as well as polynomials, scalar multiple, addition, subtraction, power, and constant, so that in your first assessment, you can assess on these earlier rules specifically. And that first assessment, I kind of want to shoot for really whenever y'all are ready. I'll let y'all do it individually. And we'll do it by video chat, so we'll have to schedule it. But we'll talk more about that in our group me or all together as a class, however we kind of do that, and for whoever wants to do that. And so that's it. So thank y'all for watching. Thank y'all for listening. Hopefully it helps. If not, let me know. Give me some feedback so I can make the next videos better, because there's going to be a lot. And most videos will hopefully be a little bit shorter. They won't be as long. I'm going to try to keep them a little bit shorter. So thank y'all, and that's it.